Hi, welcome to Unit 4, Day 11, How to Predict if a Molecule is Polar or Nonpolar. This is Part 1 review. So recall from at the beginning of this unit, we were looking at properties of metals, ionic compounds, and covalent. And for covalent molecules, in order to predict if it's soluble or not, we need to know if it was polar or nonpolar. And in the beginning of this unit, I actually told you if it was polar or nonpolar. Now you're going to learn the skills to determine that on your own based on the molecule. So yesterday we got started in that effort. We learned about polar bonds and polar molecules. And essentially a polar bond and polar molecule will have opposite ends, so a positive end and a negative end. For example, hydrochloric acid and H2CO, formaldehyde, are polar molecules. And that's because one end of each molecule is partially negative, and you can tell that where it's color-coded here in the electrostatic potential map in red, so that end is negative. And the other end is partially positive, so the end that's blue is positive. And since they have a positive and negative end, it's polar. And polar molecules like these would have what's called a molecular dipole, which is an arrow that points in the direction of the negative end of the molecule. On the other hand, CO2 is nonpolar, and that's because it has only partially negative ends. So both of its ends are partially negative. In order for it to be polar, one of these ends, either the left or the right end, has to be positive. The other thing that we learned yesterday is that it's the difference in electronegativity of atoms in a bond or in a diatomic molecule, which is a molecule with two atoms, that makes the bond polar. The more electronegative atom will have a partially negative charge because it's stronger and pulls the electrons in the bond toward it, so it's surrounded by a negative environment. On the other hand, the less electronegative atom will have a partially positive charge because the electrons are pulled away from it, so its environment is positive. And we explored this through the PhET simulation, where we had a diatomic molecule, or you can think of this as a bond with atoms A and B in it. And we were able to change electronegativities of both atoms and see if the molecule or the bond was polar or nonpolar. We also then discussed a little bit further nonpolar bonds versus polar bonds, right? So again, it's this sort of tug of war of the atoms pulling the electrons toward themselves. The other thing we learned is that when it comes down to the polar character of a bond, you can sort of think of it as being on a spectrum. And the greater the difference in electronegativity of the atoms in that bond, the more polar the bond. So if the two atoms have electronegativities that are, the difference in the electronegativities are between 0 and 0.3, we would say that that is a nonpolar covalent molecular bond. On the other hand, if the difference is between 0.3 and 2.0, it's going to be polar because it's a stronger pull from the more electronegative atom. And the greater the difference is, the more polar it becomes. Now, once it gets so extreme, their difference in electronegativity, it becomes ionic. And the last thing we learned is that for a diatomic molecule, a molecule with two atoms, or a bond, we can use a difference in electronegativity to determine if a molecule is polar or nonpolar. So before we continue with today's lesson, what we're going to do in part 1 is just review how do we use that difference in electronegativity to predict if a diatomic molecule or an individual bond in a molecule is polar. So here are our examples. In this example, we're asked which of these diatomic molecules are polar. And the steps that we do is first we'll find the electronegativity of each atom in the molecule. So we would look in this table up here. Now I've highlighted the elements that we're using in these examples. Then what we do is we will subtract their electronegativities to calculate the difference in electronegativity. And just one quick note, when you're calculating the difference in electronegativity, it's the absolute value that you're really calculating. So that means that if your difference comes out to be a negative value, you're going to flip that sign to make it positive, because signs don't matter here. So just make it, flip the sign for the difference in electronegativity and make it positive if it comes out to be negative. And then finally, we're going to use the difference in electronegativity table shown below to see if it's classified as polar or nonpolar. Now, one quick note, yesterday I had the range for a polar covalent bond between 0.3 and 1.9. I changed it to 2.0 because that's more in keeping with the examples that we see here. And the reason why I can do that sort of change is because these values, as I said, they're on a spectrum. Scientists sort of set these things up based on things that they have observed. So those numbers can change depending on the source that you're looking at. Okay, so going to this first example, we want to know if H2 is polar or nonpolar. Now, looking at it, you can probably have a sense that it's what it's going to be, but let's go through the process. So this molecule is made up of 2 hydrogen atoms. So we'll find that in the electronegativity table. And the electronegativity of hydrogen is 2.20. Then what we're going to do is subtract those two values. Since both of these atoms are hydrogen, I'm subtracting the electronegativity of the 2 hydrogen atoms. And that gives me a difference of 0. Then I'm going to go over here to this table and figure out where does that lie. So if the difference in electronegativity is 0, it's nonpolar, okay? Because it says between 0 and 0.3, it's nonpolar. And that's where we're at. All right, we can do the same thing for HCl. So in this case, we have 2 different molecules. We have hydrogen and chlorine. So I find those in the table, hydrogen and chlorine, and I write down their electronegativities. One quick note before we continue on, I just wanted to quickly note that diatomic molecules, elements like H2, F2, O2, they're always going to be nonpolar because their difference in electronegativity is 0. I meant to tell you that before. But anyway, going back to this example for HCl, I found hydrogen and chlorine in this electronegativity table. I write down the electronegativities. Then what I'm going to do is I'm just going to subtract those 2 values. I get 0.63. All right, so then I go to this table. Well, where's 0.63? It's not between 0.0 and 0.3. It's between 0.3 and 2.0. So that makes it polar covalent. So this will be a polar molecule. Doing the same thing for ClBr. So again, I find the atoms. Here's chlorine, here's bromine. I'm going to subtract these 2 electronegativities to get their difference. And when I do that, I get 0.09 as a difference electronegativity. That fits in the nonpolar range. And finally, for NO, I do the same thing. N is here, O is there. I subtract their 2 electronegativities. That gives me 0.43, and that makes it polar because it's in the polar range. So that means the answer to this question, which of these diatomic molecules is our polar, it's going to be B and D. Now I want you to try that with this CFU. Which of these diatomic molecules is or are polar? So you can pause the video now. When you press play again, the answer will be revealed. Okay, so here are the answers, A, B, and D. And this is the work that I have for that. So if you want, you can take a look at this work. So that is it for part 1 review. What we're going to do in part 2 is we're going to learn how to predict for molecules that have more than 2 atoms if they're polar or nonpolar. Have a quality day.